So I'm Kevin Sala from the Lawrence Livermore National Laboratory, and I will talk about the Instrumentor, which is a easily customizable code instrumentation for LLVM. So instrumenting code has been used widely in the last decades for tracking the runtime behavior of applications and user programs. We have been using for debugging, sanitization, logging of events, monitoring resource usage, but also for performance analysis, so we can find the performance bottlenecks and try to optimize that parse. So the instrumentation first starts with the original code from a user application. We see here a function in LLVM IR. This is the original code without the instrumentation. It takes a pointer parameter. We load from using that pointer from the memory. Then we store a value into the same memory position. And then we return the value that we have loaded. So let's say that we want to instrument the load operations and forward some information about the operation to a runtime component, a library, that will perform some processing of that information later. So we can generate the instrumentation code, instrumented code, sorry, that before the load just calls to the runtime component. It's a instrumentation call. And it passes some information about the load operation, like the pointer and the size of the access, which in this case is 4 bytes. So the main actors of the instrumentation support are first in the compilation stage, and then in the execution stage. In the first one, we have the compiler that has to augment the original code of the user with some extra code for instrumentation. As we have seen before, it has to insert some instrumentation calls. And then the runtime component, which can be a library, is the one that will receive all this information, gather it during the execution of the application, and process the data online, or just store that data on a file and then process it later in another moment. So the implementation of the instrumentation libraries will be different between the different instrumentation tools that we have. If we are doing debugging or if we are doing sanitization, the libraries will be different. That's okay. But the question is, do we actually need to do the same and re-implement the instrumentation pass in the compiler side each time that we have a new instrumentation tool? The answer is most likely yes. And that's because compilers lack generic mechanism for instrumenting the code. I mean, we can insert manually in the LLVM passes some instrumentation calls, but that's like a low-level mechanism, and we would like to have something more generic and higher level. What happens actually, and it's the case also in the LLVM compiler infrastructure, is that we have multiple passes that implement custom logic for instrumentation. Each one targets a different instrumentation tool or instrumentation library. And they are actually, in general, similar on what they want to do, but they are not enough similar in order to reuse the same pass, the instrumentation pass for all these libraries. So what we are missing here is several opportunities. We are having bad code maintainability. We have replication of code. Because we have multiple instrumentation passes doing similar things. And when you are building a new instrumentation library, you have to go to the compiler side, duplicate instrumentation pass that is already existing, and then adapt it to your needs of your instrumentation tool. So that adds some difficulties in the development of new tools. So why not we use a generic instrumentation pass that tries to be generic and customizable, and instead of having multiple of the passes like we have now, we just have one, and we can target multiple instrumentation tools or libraries. This is the task of the new Instrumentor pass in LLVM. It's somehow generic, and it can be customizable. The user can decide what to instrument, what information you want to provide to the runtime component at runtime. And then it's also extendable for LLVM developers. Like if there is some other opportunities to instrument that are worthy to have in the Instrumentor pass, they can extend it. So with this, we enable multiple uses to have with the same instrumentation pass instead of having multiple. This improves the situation that we had before. We will have now better code maintainability, less code replication, and now when you are building a new instrumentation tool, you will have just to have a configuration for the Instrumentor pass, specifying what you want to instrument, and you will not need to create a new pass from scratch to target your instrumentation tool. So let's see how the Instrumentor works. It's LLVM pass, and this Instrumentor pass works based on a JSON file that the user can provide. We have a default JSON file describing all the opportunities that we can instrument, but then you can copy that file and just adapt it to your needs. Here in this file, you specify what you want to instrument and also how you want to instrument. Let's see, the first section of the JSON file is the configuration section. There are other options inside, but the most important one is the runtime prefix, where this will be the prefix of the instrumentation functions that will be inserted into the user code. And generally, you will set here the name of your instrumentation tool or library. And then you can specify other sections saying what you want to be instrumented by this pass. For instance, if we go back to the code that we had before, the original IR of the function, and we say that we want to instrument the load operations just before they happen, we will need to create a section here saying that we want to instrument the instruction just before it happens, and then a list of instructions that we want to instrument. We are just doing it for the load operation here. We open, and then we enable the instrumentation for that instruction. And the other options are for saying what information we want to forward to the runtime component. For instance, we will want to forward the pointer. We will want to forward the size of the axis of the load operation, the alignment, and whether it is volatile. So if you run the Instrumentor pass passing this JSON file as the command line below, and you have the input of the original IR, you will get the following code below. That it will insert instrumentation function call here with the prefix that you specified, preload just before the load, and forwarding all the information that we have specified, the pointer, the axis size, alignment, and whether it is volatile, which is not in this case. Okay, so that's the basic working. Then there are some other interesting features like, okay, let's say that your instrumentation tool wants to replace some of the openings of the instruction that you are being instrumented. For instance, we want to change the pointer operand of the load that we are instrumenting. So you have to specify here in the pointer.replace, you have to specify a true. It was false before. And now it generates the same instrumented code, except that The instrumentation function now returns a pointer, which is provided by the runtime component, and then we just forward it and we use it as the pointer operand of our load operation. We have seen that these patterns are useful in some cases, for instance, in a sanitizer that we have been developing. And how does this work in the pipeline? It's just that you have your example in C, C++. You can convert it to LLVM IR using Clang. Then internally, the Instrumentor will execute if you have enabled it. It will read from the JSON config file what you want to instrument. If you didn't provide any, it will just read from the default one. And it will generate the instrumented version. And finally, you will be able to compile it and link it to your instrumentation runtime library. That is the one that will gather all the information and process it later. Here I'm showing some opportunities that we allow to instrument right now. This means that these are the instrumentation points that we allow. There are different instructions that we allow to instrument. As I said, the loads, the stores, it's similar, the options that we can forward. Then we have also the option to instrument function calls. Let's say that your original code calls the fprintf as the code there. Then the instrumentor pass will instrument that function call, notifying the runtime component about that call just before it happens. And you can specify several information about that call, like, for instance, the callee address here, the callee name, the intrinsic ID, if it's actually an intrinsic, the number of parameters of the fprintf, the pointer to the parameters. So with that, you can actually access the parameters of the fprintf just before it is called, and you can inspect them. But there is also the option to replace these parameters, like say that you want to replace some of the operands of the fprintf function call. You will be able to do it with the parameters.replace option. Then you will be able to change any of the parameters. There is also instrumentation for alloca's, passing the address, the size, the alignment, etc. The branches, compares, and some other instructions that I will not mention. We also allow instrumentation of the function enter and exit points, which is just before entering after entering the function and before exiting. And we allow also to inspect the arguments of the functions. And we also allow instrumentation of global variables and module constructor, destructor. We can also, all these opportunities can be instrumented in two positions, just before they happen or after they happen. And we use the pre and post keywords in order to distinguish between those two cases. There are other opportunities that we have used for optimizing the instrumentation, like, for instance, the loop range information. Let's say that you have the user code has a loop, and you want to perform some checks just before the loop instead of doing them inside each of the loop iterations. You can use that opportunities in order to get a function call of the instrumentation just before the loop. There are some other use cases. I'm showing some use cases here. One is the profiler. We have implemented a very simple profiler for checking the execution time and the time spent in each of the functions from a user code using the Chrome tracing tool. And the important thing here is that we only need to files to implement the profiler. This is the profiler.cpp. This is the runtime component. We only have 56 lines of code. These are the code that implements the start and stop of the watch when we enter a function and when we exit. And then we do not need any change on the compiler side. The instrumentation is done automatically by the Instrumentor pass, and we only have to provide him with a profiler.json that are like 26 lines of code. It's quite simple. I'm just showing here the JSON that we have used. We instrument the functions at the enter point and the instructions of function calls just before and after they happen. I'm showing only here an example of the runtime that we have used for the profiler. It just used the LLVM support utilities for the tracing, and we can see there the 3 functions that will be called by the user code for instrumentation. There is another example of usage of our Instrumentor. We can have a simple detector of dead and redundant stores. In the first case, we do not detect anything because the code is okay. Then we can detect with this small detector dead store situation where we write to the same global variable with different values, and we do not consume it in between. The instrumentation shows the values that are the old and the new ones. And then there is also the redundant store case where we are storing the same value, and that is also detected by the simple instrumentation tool. Again, the important thing, with a few lines of code, we implement the runtime component, and we do not need any change on the compiler side. We just provide the JSON file here, where we instrument loads and stores, providing some information like the pointer and the values that are being loaded and stored. Some extras of the Instrumentor pass. I have been explaining that we use a JSON file in order to provide the information that to know what the user wants to instrument, but that's when you are using the Instrumentor as an external user, that you don't want to touch anything on the LLVM side. But there are cases where you may have your own instrumentation pass and you want to use the features of the Instrumentor from your LLVM pass. So we allow to use the Instrumentor programmatically without the need of the JSON file with the same capabilities, but with extended features. So we can, for instance, from your LLVM pass, you can create an instance of the Instrumentor. You can then specify the opportunities that you want to instrument, like the load opportunities. You can specify here what you want to forward. Then you can specify you want it just before the load happens. Then you can specify also a callback to filter the load instructions that you want to instrument or not. So it provides you some fine-grained control of what is being instrumented. And finally, you can pass custom data to the instrumentation functions in case they are not. It's something specific to your instrumentation tool. Okay, another extra feature is that when you are doing your new instrumentation tool, you will start by defining the JSON file, saying what you want to instrument or what information you want to forward. When you have it already, it's time for building the runtime component, but this will be adding, you will have to make the implementation of the runtime component and specify the prototypes of that function with the parameter types, the parameter names, the order, etc. But the problem is that that is tedious. So you can specify here the runtime stubs file, which is, you can specify the name of a file that will be created when the Instrumentor runs. Then you can run the Instrumentor, passing that file, the JSON file, and then this will automatically generate a stub runtime for you with all the prototypes of the instrumentation functions with the correct types and return types and everything. So this will make the life better for developers of new instrumentation types. And finally, the last extra is that we allow for optimization of the instrumentation. We allow to, instead of having calls to the instrumentation library, we can provide here, using the runtime bitcode option, the name of a bitcode file that contains the implementation of your runtime component. So when the Instrumentor is running, it will perform the instrumentation, and just in the last stage of the Instrumentor, it will read from this file, and it will import the implementation of the instrumentation functions into the user code, so the function calls will just disappear. And with that, you will avoid the cost of calling to the runtime library. So as a summary and conclusion, the Instrumentor is customizable instrumentation based on LLVM. It's a unified way of instrumenting programs, and we hope that it's easy to use for users, easy to customize, but it is also easy to extend as a LLVM developer in case there are some features that are not yet implemented. This Instrumentor should try to pave the path for future instrumentation tools. And well, we have shown several use cases. Most of them were very simple, but there are other complex use cases where we have demonstrated that this Instrumentor pass has the capability of providing all the features that are needed. For instance, the input gen from Ivan Ivanov is already ported to that Instrumentor pass. And also there is a new object sanitizer for CPU and GPU code that we are implementing that is also relying on that Instrumentor pass. So that's all from my side. Thank you very much for your attention. And if you have any question, I will be happy to answer.
Thanks for the talk. My question is, so is it feasible to kind of retrofit the existing sanitizers like ASAN, TSAN? And is that, if yes, is that something you are looking into?
We have not arrived to that step yet. We should at some point check how is I'm not familiarized with the implementation of the current address sanitizer. But yeah, we should at some point try to port that into the Instrumentor if it's possible.
Okay, thank you.
We should first check what features are needed.
Thank you for the presentation. I think that's a very useful tool for everyone. One question, is the pass now part of the default optimization pipeline in Clang?
Yes, you only have to, but you have to enable it as an option.
Okay, but it always runs and then it will check if it's enabled, right?
Yes, yes.
Okay, at which part of the pipeline is it running? Like in the beginning, before, after loop optimization?
I think it's running after the optimizations, most of the optimization, because we want to get into the point that the code is already optimized. But then there is the need for applying more optimization passes after the Instrumentor pass.
Okay. Did you consider implement that as a pass plugin maybe, so that the user could decide where the pass is inserted, and we wouldn't need the extra pass in all the default cases where it's not used?
We have considered it, but we haven't done it yet. It's in the future steps.
Okay. That would be very interesting. Thank you.
Thank you.